Okay, in this video, we're going to be going through the 2016 Further Math Exam 1, which we can see up top here, 2016. And we're also going to be looking primarily or only at the data and statistics questions from this exam. Now, being exam 1, this is multiple choice only. So let's go through and have a look at them. First of all, we can see this original information is for questions 1 and 2. I'm going to have to bear that in mind. Let's read through the question. So the blood pressure, low, normal, and high, and the age, under 50 years and over 50 years or over, of 110 adults were recorded. The results are displayed in the two-way frequency table below. Let's just highlight the key information. We've got blood pressure, age, there are 110 adults, and it's a two-way frequency table. Okay, so let's go through. They're asking for a percentage of adults under 50 years of age, under 50. And if we just scroll up a little bit, that's this column here, who have high blood pressure and high. So that means there are 11 who are under 50 and have high blood pressure. So the percentage of adults under 50 years of age who have high blood pressure. Now, when we look at that, there are 11 who have high blood pressure out of a total of 58 who fit in that age category. And to make it a percentage, we have to multiply by 100. And as you can see, I've already done the calculation on the calculator. When we do that, we get 18.97 if we round it, and that's a percentage. So our answer is closest to answer B, 19%. Okay, so question 2. The variables blood pressure and age are, okay, well, let's look at blood pressure. Low, normal, and high. That's very clearly a categorical variable, and it is very clearly a ordinal variable. So when we're looking at it, let's rule out some answers that it can't be. They're not both nominal. A continuous and ordinal could be potentially, but when we look at age is broken into essentially two categories, so it's not continuous. When we look at question D, an ordinal variable and a nominal variable, respectively, well, the first one is definitely ordinal. Is the second one nominal? No, it's not. Are they both ordinal, or is the answer C, a nominal variable and an ordinal? Well, the first one is not nominal, so our answer must be B, because we have ruled out all our other answers. The reason we approached it this way is because age typically is a numerical variable, but in this case, it's been placed into categories rather than asking for a response. And the way that we can check that is if someone was to ask on a survey, how old are you? If you're giving a number and only a number as your answer, then it would be numerical data. But because you're giving a category, you are under 50 or over 50. That makes it a categorical variable, and because it is under and over, there is a sense of order to it. So they're both ordinal variables. Let's move on to question 3. Okay, so the STEM plot below displays 30 temperatures recorded at a weather station. Now, it's very unlikely that they're going to put the number 30 in there for a random reason. And as we can see, the question says the modal temperature is what? Okay, well, the reason they put in 30 is because in order to find the modal temperature, we're going to need to find the most common. So if we look at what there is, we've got 37 appears 4 times. 37 appearing 4 times, or actually 3.7, beg your pardon. Then we've got 20 or 2.8 appears 1, 2, 3, 4, 5, 6 times. I've got 2.9 appears 4 times. So that's separate. We've got 3.4 appears 3 times. And you can very quickly see there's not enough for anything else. So the modal temperature must be 2.8. So modal referring to the most common. Now, the reason for putting 30 in there is we can very quickly see that, okay, if we've got 6, it's probably most likely to be most common, but as soon as we've got 6 and then another 8, we've used basically almost half of our temperatures, it's unlikely There's going to be something more common with what's remaining. But that also could be thrown in there to confuse us. When we see 30 temperatures and we read modal, or what happens if we accidentally try and calculate the median and say, oh, the median will be between the 15th and the 16th. That's a distractor. So we don't want to do that. We want to double check our answer. Yes, we've chosen the mode. Okay, and you'll also notice as well, it's helpful to read the key before going any further into a question. So let's look at the next question. The information we've been given relates to questions 4 and 5. The weights, so again, let's highlight that. The weights of male players in a basketball competition are approximately normally distributed with a mean of 78.6 kilograms and a standard deviation of 9.3 kilograms. Okay, question 4. There are 546 male players in the competition. The expected number of male players in the competition with weights above 60 kilograms is closest to. Okay, when we're dealing with a normal distribution, what we're going to be doing is we are going to be looking for the mean, first of all. So the mean was 78.6. And how many times do we have to go above the mean or below the mean to get to 60? So 78.6, if we subtract 2 lots of 9.3, that takes us to 60. So that tells us that 60 is 2 standard deviations below the mean. Now, if we remember the normal distribution, and let me try and draw that a bit wider. We've got our mean, then we've got 1 standard deviation. Everything between there is 68%. And we've got a second standard deviation. Everything between them is 95%. So anything below is just 2.5%. Anything below 2 standard deviations. So to find the expected number, it is 25%, or there's a few ways we could do that. 25 out of 100 multiplied by the number of players, which is 456. Beg your pardon, it is not 25%, it is 2.5%. So in our calculator, 2.5, and again, it's going to be divided by 100, and then multiply our answer by 456. This gives us an expected number of 11.4. Now they've asked us to round that to the nearest or the closest number. So closest to 11 is going to be, 11.4 is going to be 11. Okay, let's have a look at question 5, which again is going to be related. Brett and Sanjeeva both play in the basketball competition. When the weights of all players in the competition are considered, Brett has a standardized weight of this z-score, negative 0.96, and Sanjeeva has a standardized weight of a z-score of negative 0.26. Which one of the following statements is not true? Okay, you can see they've highlighted the word not, and the reason I've highlighted it again, they've put it in bold and I've highlighted it, is because it's very easy. If the first question is true, it's very easy to read it and think, oh, that's true. I'm just going to circle that and move on. You need to make sure you take note of when they say something is not true. So let's go through and try and eliminate ones that are true. Brett and Sanjeeva are both below the mean weight of players in the basketball competition. Well, that is true, because they both have negative z-scores. So we're not interested in that. Sanjeeva weighs more than Brett. Well, Sanjeeva has a lower z-score, meaning Sanjeeva is closer to the mean. And since they're both below the mean, Sanjeeva is weighing more than Brett, so that is also not what we're interested in. If Sanjeeva increases his weight by 2 kilograms, he would be above the mean weight for players in the basketball competition. Okay, let's go back up and we're going to need to check our data that we've been given. Standard deviation is 9.3 kilograms. So if he increases his weight by 2 kilograms, he's nearly a whole standard deviation below. So he's not going to be able to overcome a whole standard deviation with just 2 kilogram increase. So this is correct, actually. That's what we want. Let's just double check our last two. Brett weighs more than 68. Well, 68 was the mean. He's clearly less. And last of all, more than 50% of the players in the basketball competition weigh more than Sanjeeva. Well, that's also true, so we don't want that. So our answer would be C. Now, I've just got to be careful with questions like this because questions like this are often double negative sorts of questions. So we're looking for the one statement in here which is incorrect. And you can see that I'm crossing out the ones that are correct, which can be a little confusing. So just be careful. Think about this question before you finally circle or choose an answer. Okay, question 6. So this is some new data coming up. The histogram below, so first of all, it's a histogram, shows the distribution of the number of billionaires per million people, 53 countries. So we've got the number of billionaires and we've got frequency. So this is univariate data and it's a histogram. Using the histogram, the percentage of these 53 countries with less than 2 billionaires per million people is closest to. All right, well, they're interested in how many is less. So let's have a look. They've told us there are 53 countries. If we look really closely at the scale, it appears that there are 49 countries that are less, have less than 2. Let's just double check. We've got 2 in this column, 1 here, 1 here. So when we add up 49 plus 2 plus 1 plus 1, we get 53. So there are 49 countries. Again, we're doing a simple percentage calculation. Multiply this by 100. And when we do this, we get 49 divided by 53. Divide by 53. Multiply by 100. And we just want to convert that into a decimal. So our answer is 92.45%. And again, they're saying is closest to. So what is the number that's closest to 92? Well, it's going to be D, 92%. Okay, let's keep going. Question 7. Again, we're dealing with a histogram. So the histogram below shows the distribution of, again, the number of billionaires per million people for the same 53 countries in question 6, but this time plotted on a log 10 scale. So you can see the log 10 based on the number of billionaires. Based on this histogram, the number of countries with 1 or more billionaires per million people is what? Well, how do we work out how many people have how many countries have 1 or more billionaires? Well, let's say they've got 1. If we do log base 10 of 1, what's that equal to? Well, let's actually check on our calculator, but we should hopefully know this. If we do log base 10 of 1, the answer is 0. So we're looking at this line here. How many countries have more than 0 on this graph? Well, if we look on the horizontal axis, we've got 9 in here, and we appear to have 1 here. So it looks like we've got 10. Now, we'd want to be careful to make sure that this is a 9 and actually draw a line across just to make sure. It is 9, and then we do have 1 at the end, and we can draw a line across that one as well, just to make sure. All right, so let's move on to question 8. So question 8 is going to be a question looking at bivariate data. And the reason we can say that is because it starts off by saying parallel box plots would be an appropriate graphing tool to investigate the association between monthly median rainfall in milliliters and what? So if we look at what monthly median rainfall in milliliters is, that is going to be numerical data. Now, if you remember about parallel box plots, they are comparing numerical data and they should be comparing one numerical variable with one categorical variable. So which of these has a categorical variable? Well, monthly median wind speed, that is not categorical. Monthly median temperature in degrees, that's not categorical. Month of the year, okay, that is categorical. And the other two in hours and millimeters are not. So our answer is C. But a key piece of information, parallel box plots compare one numerical variable with one categorical variable. Let's move on. So again, we've got some information pertaining to two questions, questions 9 and 10. The scatter plot below shows life expectancy in years plotted against Human Development Index, HDI, for a large number of countries in 2011. The least squares line has been fitted to the data and resulting residual plot is also shown. The equation of this least squares line is this. So they've given us the equation and they've told us the coefficient of determination r squared. Okay, so question 9. Given the information above, which of the following statements again is not true? So we're going to need to go through and eliminate the ones that are true. So the value of the correlation coefficient is close to 0.94. So they've given us the r squared value. So to find the correlation coefficient, we have to find the square root of that r squared value. So again, let's put this into our calculator. Square root of 0.875. That takes us to 0.935. That's approximately 0.94. This is correct. So because it's true, it's not the answer we're interested in. 12.5% of the variation in life expectancy is not explained. So we've got double knots, not explained by the variation in HDI. Well, how do we work that out? We know that from the r squared value, 87.5% is explained. So 12.5% is not explained. That's correct, meaning it's not the answer we want because we want the one that's not true. Option C, on average, life expectancy increases by 43 years for each 10-point increase in the Human Development Index. Well, that's talking about the gradient. Okay, so the gradient in here is 0.422. But they're not talking about the gradient, they're talking about this number in here. So this question C is actually what we want because question C is not true. So that would be our answer, but let's just check D and E. Ignoring any outliers, the association between life expectancy and HDI can be described as strong, positive, and linear. Well, let's have a look. Ignoring any outliers, is it strong? Is it positive? Is it linear? It's strong, it's clearly positive, and it looks linear to me. So that would be correct, meaning it's not the one we want. And last of all, using the least squares line to predict the life expectancy in a country with a Human Development Index of 75 is an example of interpolation. Well, yep, 75 is within the data we've been given. So it is an example of interpolation, so that's not the answer we want. Lots of double negatives. Just be careful of them. So, question 10. In 2011, life expectancy in Australia was 81.8 years, and the Human Development Index was 92.9. When the least squares line is used to predict the life expectancy, so least squares line is used, in Australia, the residual is closest to. So remember residual, I'm just going to use shorthand here, residual is equal to the actual minus the predicted. Okay, so the actual is 81.8. And the predicted is going to be what we get when we put 92.9 into our equation. So let's go back up and look. Life expectancy is equal to 43.0 plus 0.422 times by the HDI, which in this case was 92.9. And that gives us 82.2038 was the predicted. So 82.2038. And that gives us a residual of 81.8. Subtract our answer. And that gives us a residual of negative 0.4038. What is that closest to? Negative 0.4. Our answer is B. And you can see there are some distractors in there because question C is very similar but without the negative. And then some of these other distractors will be in there if we have put the wrong numbers into our formulas. Let's move on to question 11. The table below gives, again, the HDI and the mean number of children per woman. The mean number of children per woman, and that's children, for 14 countries. The scatter plot of the data is shown. All right, so they've shown us the scatter plot, they've given us the data. Let's have a look. This question only appears to relate to question 11, this information. Scatter plot is nonlinear. Okay, a log transformation is applied to the variable children can be used to linearize the scatter plot. With HDI as the explanatory variable, the equation of the least squares line fitted to the linearized data is closest to. So in order to answer this question, we're going to need to put this data into our calculator, and then we're going to need to find the least squares regression. So let's actually open up a new page, a data and stats page. Now we're going to put two columns in here, HDI and children. And we're going to copy in all that information. So we've got 27.3, 31.3, 39.5, 41.6, 44.0, 50.8, 52.3, 62.5, 69.1, 74.6, 78.9, 85.6, 92.0, and 83.4. There are 14 data points, as we were told. And then for children, we've got 7.6, 6.1, 4.9, 3.9, 3.8, 4.3, 2.7, 3.0, 2.4, 2.1, 0.9, 1.8, 1.9, and 1.6. Okay, so we've got all our data, and they've told us that they're taking a log of the children. So let's call it log children. And in this column here is equal to, and control to get the log base 10 of children. Press enter. And when we do that, we have got all of our data. Now to find the least squares regression line, there are a couple of ways we could do it. I'm going to go into the data and stats page, put in here our HDI, and then put in here our log children. And it looks pretty linear now. So let's go menu, analyze, regression, and let's go show linear, a plus bx. And they've given us the equation. So let's then, using that equation, pick our answer. So we have our equation in terms of y and x. So we have y is equal to, now what was y referring to? That was log children. So we have log children. That was our y value, is equal to 1.05 minus 0.009 times x. And x was referring to HDI, so HDI. So which of our equations that we've been given looks like that? Well, three of them start with log children. And they've rounded it to one decimal place, so this will be 1.1. Let's just round that. 1.1. So log children is equal to 1.1. Seems to indicate that only answer A is correct so far, minus 0.0095 times HDI. Well, our answer is clearly A. All the others don't work for one reason or the other. Okay, so let's go through question 12. So in question 12, we have, there is a strong positive association between the country's Human Development Index and its carbon dioxide emissions. From this information, it can be included that what? So now we're looking for one of these that's true. So it's a strong positive association. So increasing a country's carbon dioxide emissions will increase the HDI for the country. Well, if it's a positive association would be saying that an increase in HDI would result in an increase in carbon dioxide. But then we need to talk about explanatory and response. So the HDI would be presumably the explanatory, and the carbon dioxide would be presumably the response. So let's come back to that. It could be A, but let's come back to that because we want to choose the best answer. Question B, decreasing a country's carbon dioxide emissions will increase the HDI. Well, that's not true because there is a positive association. An increase in one variable is associated with an increase in the other. And again, option C, this association must be a chance occurrence and can be safely ignored. This is, oops, sorry, I didn't mean to choose B. I meant to say it's not B. Well, it's not C either. It can't be ignored because it is a strong association. Countries that have a higher HDI tend to have higher levels of carbon dioxide emissions. Well, that would be true. And the reason that would be true is because it is a strong positive association, meaning an increase in HDI matches an increase in carbon dioxide. So this one will be true. And that makes A not true and E probably not true. Let's go through E. Countries that have higher HDI indices tend to have lower levels of carbon dioxide emissions. That's not true, again, for the same reason that it's positive. But let's just quickly look at A. Why is A different to D? So D is our answer, but why is A different? That was originally a question mark, and now we've said it's not true. The difference between them, in D, countries that have higher human development indices tend to have high levels of carbon dioxide emissions. That's different from A, which says increasing a country's carbon dioxide emissions will increase the HDI index of that country. So the main difference is causation. Option D says there is a relationship, there is an association, and that it is a positive association. Option A is talking about causation, saying if you increase one, you will increase the other. Now, that's not guaranteed because it is not a perfect positive association. It is a stronger positive association. And the other reason why it's not guaranteed is because it depends on which is the explanatory, which is the response. If your carbon dioxide emissions is explanatory for your HDI, then that makes sense. If it's not the explanatory, then it doesn't make sense. But it's the difference between the wording of a association and something tending to increase as opposed to a definite will always increase. Okay, so let's look at question 13. We're dealing now with time series data. So consider the time series plot below. Let's just have a look. We've got month number and we've got mean temp. And we can see that's going up and down quite a lot. The pattern in the time series plot shown above is best described as having what? So there are 5 options, irregular fluctuations only. I would strongly disagree with that. And the reason we can disagree is because we can look at the troughs. If we look at the troughs, where are our troughs occurring? They're occurring very consistently. And we've got 4 troughs over a period of 48 months. We've got 4 peaks. It is definitely not irregular. So this is not true. An increasing trend with irregular fluctuations. Well, that's definitely not an increasing trend. Although there is an increase in the peak, the troughs are basically the same. And if we were to take a line of best fit through the middle, we would actually find that it stays pretty consistent. And even though the peak did increase, it then goes back down again. So it's not B either. Seasonality with irregular fluctuations. That's a possibility. We'll come back to that. It's definitely got seasonality. Let's have a look at D and E. So seasonality with an increasing trend and irregular fluctuations. Well, there's no increasing trend, as we said before. E, seasonality with a decreasing trend and irregular fluctuations. Well, it's not that, so it must actually be C, that it's got seasonality with irregular fluctuations. And just to confirm, let's just look at these fluctuations as examples of those irregular fluctuations, even though they're small. Okay, let's keep going. So this information here applies to questions 14 to 16, which takes us to the end of the section we're doing in this video. So the table below shows the long-term average of the number of meals served a day at a restaurant. Also shown is the daily seasonal index from Monday through Friday. Okay, so we've got Monday through Friday seasonal indices and long-term averages. Question 14. The seasonal index for Wednesday is 0.8. This tells us that on average, the number of meals served on Wednesday is what? Well, that would be saying it is 84% of what it is in the long term. So 84% of the average daily serving. So it is either 84% of the average, or we could say that is 16% below average. Let's have a look. So it appears that A would be our answer, 16% less than the daily average, but let's go through. 84% less than the daily average. No, it's not less than. It's not 84% less than. It would be 84% of. It is definitely not the same as the daily average. It is definitely not more than the daily average. So both of them are wrong, so our answer is A. Let's move on to question 15. Last Tuesday, 108 meals. 108 meals were served in the restaurant on Tuesday. The deseasonalized number of meals served last Tuesday was closest to. Okay, so there was 108 meals served in the restaurant. That was what was served on Tuesday last week. If we look at the long-term average, it's 93. But if we look at the seasonal index is 0.71. Okay, now how do we deseasonalize a particular data point? Well, we take it and we divide it by the seasonal indice. And when we do this, if we just go back to our calculator page, when we do this, we have 108 divided by 0.71. And that gives us 152.113. And that is closest to 152, so our answer would be E. And last but not least, the seasonal index for Saturday is closest to. So they're asking us to find the seasonal index for Saturday. And again, closest to. How do we work this out? Well, we can work out our long-term averages, and then we can work out, based on that, what our seasonal indices are being calculated from. So if our long-term average is 89, then our seasonal index, 89 divided by our seasonal index, should give us the long-term average of every day, because that's reversing how it's normally found. So take 89, our long-term average, 89, and I'm just choosing a particular day. In this case, I'm choosing Monday, and divide it by 0.68. If I do that, 89 on the calculator, divide by 0.68, gives us 130.882. Oops. And that is the average across all of the days. And then for Saturday, they get 190. So to find our seasonal index for Saturday, it will be 190 divided by 130.882. So 190 divided by 130.882. When we do that, we get 1.45, and that is closest to 1.45. So D would be our answer. Okay, if we really wanted to check, we could go through and check our answer and put 1.45 in here and do the same process for Sunday. And if we did the same process for Sunday, we should get a number in here such that all of our seasonal indices should add up to 7 if we were to add them together. So let's just do a quick Sunday calculation. So on Sunday we have 160. 160 divided by what the daily average is, which is 130.882. So 1.22 would be our rounded seasonal index. 1.22. And if we just want to check that we've got our answers correct, we do 0.68 plus 0.71. So just to be clear, I'm adding together all my seasonal indices. Plus 0.84 plus 1.01 plus 1.10 plus 1.45 plus 1.22. And if we do that, that adds up to 7.01. And the reason we can assume that we're correct is because we would have rounded these two values, and we probably would have rounded all these values to keep them to 2 decimal places. So the fact that we're 0.1 off, we're not concerned about. So that would make sure that our answer for question 16 is correct. All right, that brings us to the end of the data and stats questions from the 2016 exam 1. And in other videos, we'll be going through different questions.